Hi, everyone. Hope everyone's doing well. Where we left off last time was kind of a big section. We just finished a section on solving exponential and log equations. So I hope that you've had some time to review that video and try some practice problems. That can be a tricky section. So, remember, you can always go back and watch the video a second time or go back and reference parts of it, but try some practice problems and see what you can do. Once you feel comfortable with that, this video is going to talk about modeling with exponential and log functions. This section is going to be a little shorter than that one was. And it's basically word problems, some real life applications. We've already seen some real life applications, some word problems, right? In this chapter, in this, section of topics, because we've seen already that you can use exponential functions for interest. We've seen towards the end of the last video, we used logs to help us solve a problem that had to do with interest. And I think at some point we also had a problem involving decibels of how loud a sound was, and that used logarithms. So, interest and loudness of a sound, we're going to see a couple more real life applications here. All right, so besides interest and the loudness of a sound, modeling with exponential and log functions, one of the popular things that exponentials can be used for is population growth. And this could mean the growth of a population of humans, but it could also be the growth of a population of some other animal or bacteria or anything. Let's see. I'll show you. There's several models exist. I'll show you two examples. Two examples. They're both going to use exponentials in a way. There's a simple exponential growth model for population. And it says n of t equals n sub 0 2 raised to the t over a. And I should tell you what some of these things mean, where n sub 0 is the initial population, and a is the time it takes to double. And n of t is the number of individuals after t time has passed. Size of the population. Now, this is exponential. You see that it's 2 raised to a power. And what winds up happening, we could graph this. I guess we wouldn't really call it like an x-axis and a y-axis because there's no x's and y's in this equation. We could say that this is the t-axis, the amount of time that has passed, because this is a function of t, so that should be on the horizontal axis. The vertical axis, maybe I'll just call that n. And this would look something like an exponential curve that goes up and up and up and up. And it started at a value of n sub 0. Okay, so population doesn't really start at 0. It starts at some positive number, and then it goes up and up and up exponentially. So that's one model that can be used for population growth. In real life, populations do grow somewhat exponentially at first, but they might not grow like that forever. I mean, is it realistic to say that this curve is just going to keep going up and up and up exponentially without any kind of upper bound without any kind of limit. So another type of growth model that exists is called the logistic growth model. And it tries to address this issue. It tries to make a model that's a little bit more realistic. And it says P of t equals d over 1 plus k e to the negative ct where d, k, and c are constants specific to the problem. This growth model is more complicated. The formula is more complicated. It has more constants, and the d, k, and c can have to do with things like the amount of resources available to the population, the amount of room that they have to grow, things like that. But what winds up happening if you try to graph this is you get what might be considered a more realistic curve. Now, there's still a t-axis for time. I guess I'll call the vertical axis p, since that's what we called the function. Let's see if I can draw this. It's actually going to have a horizontal asymptote. And what winds up happening is you get a curve that starts at some non-zero value, and it goes upward, and it goes upward exponentially at first. Okay, so it starts going exponential, but there's going to be kind of some limiting factors. You might imagine that there's a population of prey, and then maybe there's some predators, that are going to keep the population below a certain amount. Or you could just say there's no predators, but maybe there's a limited amount of space or a limited amount of food. So population tends to kind of level off. It started off looking like it was going to grow exponentially, but instead of growing exponentially forever, there are factors at play, which are kind of built into these constants. There are factors at play that are going to make the population almost reach a plateau. It approaches this asymptote, but it never exactly touches it. Now, I'm going to say you don't have to memorize these formulas. These are two examples of population models. There are also other ones, and you don't have to memorize these. If there's going to be a population problem, then I think that the formula would be given in the problem. And I'm about to show you one, and it'll give us the formula. So for example, a bacteria colony grows according to this growth model, where the initial population is 100 individuals, and the population doubles every 2 hours. Now, something I didn't say, but maybe you're starting to see it, is that t could be measured in hours, or it could be measured in some other length of time. We didn't really specify like we did with the interest problems. In the interest problems, t was always measured in years. In these problems, that's not necessarily the case. T could be hours or minutes or days or years. Depends what the problem tells you. So I haven't really asked a problem yet, but I'm going to have two questions for this that I'll talk about. Part A, what is the population? after 7 hours. And part B, when is the population 10,000? And I'm going to talk us through this. I'll tell you that I find part B to be more interesting. Because it's asking when. The when problems, I think, are more interesting. Okay, so we imagine this is growing according to a simple growth model, and part A is really just asking us to find n of 7, right? It says, what's the population after 7 hours? So n of 7 is going to be 100 times 2 to the 7 over 2. Whatever this equals, that's going to be our answer. I found with a calculator, this is approximately 1,131. And I'm going to tell you that I rounded this off to the nearest integer because this represents a number of bacteria. You know, I didn't want to say that we have some fraction of a bacterium, so round it off to the nearest individual. You do the same thing if you're talking about some kind of animal population. Round it off to the nearest individual. All right, that's it for part A. Part B is where it gets more interesting. So it's asking, when will the population be 10,000? We know the formula that we're using. We want n of t to be 10,000. So we could set up 10,000 equals 100 times 2 to the t over 2. And we want to solve for t. T is the unknown. It's the only unknown in this whole thing. Okay, first things first, do not multiply the 100 times 2. Do not combine those to be 200. That would be an algebra mistake. Because order of operations says exponentiation comes first. So like 2 raised to a power, like that is 2 raised to a power is an object. And then it's getting multiplied by 100. So it would not be the same thing as turning this into a 200. Just like when we did interest and we would have like p e to the rt, we don't multiply p times e and then raise it to the rt, you know? Okay, so what I'm going to do, I want to deal with the 100. Let's just divide both sides by 100. So divide both sides by 100, and it simplifies things. Like that. What can we do now? It's an exponential equation. We talked about solving these. How about we do a logarithm with base 2 and say that log base 2 of 100 equals t over 2. Makes sense, right? We're trying to solve for t. We almost have it. T is 2 log base 2 of 100. And then because this was a real-life problem, I went ahead and I found this with a calculator, and I found this to be, you know, if this was the type of problem, like if we were doing a test where I wasn't allowed to use a calculator, I would just put a box around this and say we're done. The answer is 2 log base 2, 100. Okay, but I found this with a calculator to be about 13.23 hours. It takes about that long for the population to be 10,000, which is pretty impressive. Population of bacteria does tend to grow very rapidly. So we started with only 100 bacteria, and we have 10,000 bacteria only 13 hours later. Let's move some of that. to say note, this problem used 2 raised to a power, and we wound up doing a logarithm with base 2. I'm going to say base 2 and doubling time are convenient. You know, this problem told us that the population doubles every 2 hours. That's why everything is centered around base 2. Another option that's sometimes used in the sciences is base E. And in that case, we get a different looking model, or a different looking formula, n sub 0 e to the RT. And I'm going to say where R equals the relative rate of growth. So I guess this is the third, earlier I said that I was going to give, I said several models exist. I was going to give 2 examples. We had the simple exponential model. We had the logistic growth model. This is kind of a third one. This is kind of a variation on the simple exponential growth model. It's a base E version of that model. Now, when I say R is the relative rate of growth, I'm going to say, for example, if R equals 0.03, then the growth rate is always 3% of the population. So instead of being based on how long it takes to double, it's based on a percentage of the population. And this should look familiar to you. This is not just a coincidence that this looks a lot like the interest formula. It looks a lot like P e to the RT. I mean, that was for continuously compounded interest. The number out front was P, which was the principal. But if you think about it, the principal was really just the starting amount. N sub 0 is also sort of the starting amount in a certain sense. It's the starting population. So let me show you a problem where we're going to use this version of the model. Okay? Example. And I'll tell you, we're going to use this model, so I'm not going to write the formula again. Let's say that there are initially 400 bacteria. And the population grows by 25% per hour. So, okay, just in my head, I could figure out, like after 1 hour, I can figure out what the population would be. But we could use the formula to answer more complicated questions. I'm going to give you 2 questions and give you a minute to try it. First of all, what is the population after 8 hours? And secondly, when is the population $30,000? So I'd like you to pause the video, take a minute, and see if you can answer this one. Okay, so again, I think part A will be kind of quick. Part B will be the more interesting one. Part A is just asking us what is n of 8, and we're using that formula from above. Starting amount is 400. E raised to the 0.25 times 8. 0.25, so that's a fourth of 8, so it's 400e squared. So if, again, if this was like a test where we weren't allowed to use a calculator, we would just put a box around it and say this is the answer. But for the purposes of this discussion, I did find this with a calculator. I rounded it off to the nearest individual, 2,956 bacteria. Is that a lot? I mean, we started with 400, so you imagine a little colony of 400 bacteria. It's grown to almost 3,000 after only 8 hours. Part B is asking, when is the population 30,000? Well, I know that it's definitely going to be more than 8 hours, because after 8 hours, this was the population. So we need to keep going for a while longer than that. We know what the population should be, so we set 30,000 equal to the formula, 400 e to the 0.25 t, and we want to solve for t, right? Solve for t. Let's divide both sides by 400. 400 going into 30,000 should give you 75. So I get ln 75 equals 0.25 t. And then I say, well, 0.25 is just 1/4. Let's just multiply both sides by 4. So t is 4 ln 75. I found with a calculator that this is approximately 17.27 hours. That is how long it takes. Okay, so those were a couple of population growth problems. I want to show you another application. Let's talk about radioactive decay. Radioactive decay. So for population, we talked about a couple of different models, but for the first one that we did, the simple exponential growth model, the first one with the 2 raised to the t over a, we used time to double. And we had one word problem where I said, the population takes 2 hours to double. So that was a factor. Now we use time to reduce by half, because we are going to be talking about radioactive decay. So there's going to be some substance that is reducing. Instead of growing, it's reducing. And this is also known as half-life, the half-life of the substance. And it gives us a model for the mass of a decaying substance. The idea is that if something is decaying, it's getting smaller in size and volume and also in mass. So the mass will be measured by m, and we're going to say m of t equals, this is going to look like that simple exponential growth model for population. But instead of growing, we want it to reduce. It's going to be m sub 0 times 2 to the negative t over h. I keep writing all these formulas today. Maybe I'll put a box around this. I'm saying you don't need to memorize these. They would be given in a problem. Oh, and let me tell you that this is where h equals half-life. It's the length of time that it takes to reduce by half, and it is sometimes sometimes done with the Greek letter lambda. Looks like that. By the way, if you were to graph this, what would it look like if you graphed this? I guess we'd have a t-axis because t is the variable. We'd have an m-axis because m is the name of the function. The idea is that the mass starts at some amount, m sub 0, and over time the mass decreases. Like that. There's some length of time that it takes for the mass to reduce by half. So for population, we had the version that was based on how long it takes to double, and then we had the version that was based on the relative rate of growth. So here's a question. What if we want to use base e? What if we want to do this but use base e? Can we do that? If we want to use like a rewritten version of this that has base e and negative RT, I'm trying to do something that's kind of like an analog to like the two different population models. Can we have two different radioactive decay models? If we want to do this, then what is R? Like in particular, how is R related to H, the half-life? Well, I'll show you. We can derive a really simple rule really quickly too. We want the mass to divide in half when the half-life has elapsed. So initial mass in half equals the initial mass times e to the negative RH all right, half the mass remains. That's the amount that we started with. The amount of time that has passed is the half-life. We could divide both sides by m sub 0. M sub 0 is some number. Divide both sides by it, and the left-hand side becomes 1/2. We get this. From this, I could do ln of both sides maybe because there's e to a power. Let's do ln of both sides. ln 1/2 equals, if I do ln of the right-hand side, it's going to simplify to just negative RH. And from this, we get the little formula R equals ln 2 over H. I'm going to put a little box around this too. So you can see it all on the screen right now. There's the mass of a radioactive decaying substance using a formula where you need to know the half-life. Okay? And then there's this other version of it that's based on E instead. And this is how R and H are related to each other. I would say that the key idea is that if we are given the half-life of a substance, we have a choice. We can work with base 2, or we can work with base E. Working with base E requires the extra step of solving for R using this little formula. But it might be preferable in some cases. For example, if you have a calculator that can only do base E. You know, some calculators can't do logarithms with base 2, but they can do logarithms with base E, and that's where this comes in. All right, I'll show you a word problem example. Example. Polonium 210 has a half-life of 140 days, given a sample with mass 200 milligrams, there's going to be a few parts to this. Part A. Part A, write as m of t equals m sub 0 2 to the negative th. Part B, write as the other one, m of t equals m sub 0 e to the negative rt. And part C, I think I'll talk us through this one once I get it all written down. Part C, when will the mass be 60 milligrams? I'll give you a chance to write this down, though. All right, we need a fresh sheet of paper for this, I think. I think part A and B will be quick. Really, the whole thing won't be too bad. Oh, and by the way, we're using the stuff from above, so even though this problem didn't give it to us, you know, we know R equals ln 2 over h could be used here. Okay, so one thing I want to warn you about is whenever you get a word problem, it's up to you to kind of decipher which information here is needed, and is there anything that's kind of extra that's not needed. And in particular, like which numbers do we need to use? Polonium 210 is the name of the substance. We're not actually going to use the number 210 for anything. That's just a part of the name. Okay, that's the name of what we're dealing with. So polonium 210, we're not using the 210 anywhere. Let's jump into part A. And we want to do m of t equals, we know the initial mass that's given is 200. So 200 times 2 to the negative t over the half-life was given as 140. That's it for part A. Part A just wanted us to write the formula with all the little pieces that were given. Part B wants us to write it in the other form, and in the other form, we need to find out what R is. But remember, R equals ln 2 over h. H was given to us as 140. So we get m of t equals 200 e raised to the negative r, right? Negative r. What did we just find for r? So ln 2 over 140, and this should be times t. We could just write it like that. We did write it in the form that it asked us to. And part C wants us to answer one of these. When will blank happen? You know, the problems where we probably have to solve something for t. So we want the mass to be 60. It turns out that we could use either one of these equations, the one from part A or the one from part B. In my work on my page, I decided to use the one from part B. So we want the mass to be 60, so let's say 60 equals 200 is the starting amount, and then e to the negative ln 2 over 140 times t. We are going to solve for t. Looking at the problem, it looks like the half-life was measured in days. So if we solve for t, we're going to get t in days. T is going to be measured in days. what do we usually do first with these types of problems? Divide both sides. Let's divide both sides by 200 to get the 200 out of here. So we're going to have 60 over 200. We could either deal with that as a fraction. I guess 6 over 20. 6 over 20 is the same as 3 over 10, or 0.3. So, I mean, you could write that as 3 over 10, but I wrote it as 0.3. So, I think I'm going to do the thing where I say this means something in terms of logarithms. E raised to a number equals something is the same as ln of this something equals negative ln 2 over 140 times t. Remember what we're trying to do. We're trying to solve for t. We're basically one step away. T equals. What do we need to do to this to get t by itself? We've got this messy looking thing here. Do we want to divide both sides by this fraction? Well, we could. But instead of dividing by a fraction, we could multiply by the reciprocal. I prefer that. Multiply by the reciprocal. So negative 140 ln 0.3 over ln 2. And that's going to be my answer. I could get this far without a calculator. I could put a box around it, say that's my answer. But I also found this as a decimal. And I found that this is approximately 243 days. So we've got a sample of polonium. You could kind of do a little bit of a reality check and say, does this make sense? We were told that the half-life was 140 days. We started with 200 milligrams. So I would expect that after 140 days, we would have half of what we started with. So we would have 100, right? Let me write some of this. Note. Starting amount, 200 milligrams. Half-life, 140 days. So after, I realize you can't see that. All right, so after 140 days, we have mass equals 100 milligrams. After a total of 280 days, like 2 half-lives have passed, the mass, in the first 140 days, the mass dropped from 200 to 100. In the next 140 days, it drops from 100 to 50. So our answer of 243 days makes sense to get 60 milligrams. Sometimes with, word problems, I like to try to do a reality check like that. Do these numbers all kind of make sense with what we know? Half-life means we drop from 200 to 100 to 50. It takes 280 days to drop down to 50. This problem was asking us not about 50, it was asking us about 60. So the answer that we got was a little bit less than 280 days. It was 243 days. If you ever do a word problem and you try to make sense of it and check to make sure it makes sense, and you see that it doesn't make sense, like if we got an answer that was something like 5,000 days, we would think about it and say that can't be right. And then you would kind of take a couple of steps back and see where you went wrong. On the other hand, if you got a really small answer, if you got something like 7 days, You would say 7 days can't be right. It takes 140 days just to get down to 100. So try to do that when you can. That was all kind of a side note. We answered the problem up above. So that was a brief lesson on some modeling with exponential and logarithms. And, we basically looked at population growth, a couple of different models, and radioactive decay, a couple of different models. Previously, we had seen, interest problems and one problem about decibels. You could also get some unique problems that show up. Uh, Another application that we didn't really talk about in these videos is called Newton's law of cooling. It has to do with how long it takes for a hot object to cool down. I think that there might be some, you could get a unique problem where maybe a formula is given to you, and it's not about memorizing formulas. It's about being able to read a word problem, understand what it's asking for, and then maybe you have to solve for t or solve some kind of little equation. So that's really what this section is about. All right, so that's it for this section, and that is actually going to be it for our discussion of exponentials and logarithms. So in the next video, we're going to jump to a very different topic. So now's a good time to kind of go back and review all this stuff about exponentials and logs. Make sure you feel good about it, and then in the next lesson, we're going to get kind of a fresh start on a brand new topic. Okay, so I will see you then. Take care, everyone.